Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering at Institute of Aeronautical Engineering. So in today's class, we are going to discuss about the topic magnetic coupled circuits. So in the previous classes, we have already discussed some basics about the magnetic coupled circuits, which is what is the Faraday's law of electromagnetic induction and what is self-induction and mutual induction. So here to get understand better about the concept of mutual inductance, it is very important to go through these magnetic coupled circuits. And of course here, first let me discuss about some basics about the magnetic coupled circuits. So the coupled circuits is nothing but, okay, so when the two circuits are placed nearby, okay, here as you can see here, so let us consider here this is circuit 1 and this is circuit 2. So we have placed these two circuits near to each other, so that the magnetic flux produced by the one circuit is linking with the another circuit. So due to the magnetic flux linked with the another circuit, so there will be a EMF produced in the other circuit, which is the secondary circuit. So how this thing will happen because of this coupling between these two circuits. So the coupling here, it is the magnetic coupling, right? So which means, so here let us consider here E1 is the EMF induced in the circuit 1 and E2 is the EMF induced in the circuit 2. So anyway here we are just applying an EMF E1 to the primary circuit or the circuit 1, then there will be a current flow through this particular circuit, which means there is a change in current which is flowing through the circuit 1. So due to this the magnetic field or the magnetic field produced within this circuit 1. So this is called as the magnetic field produced by the circuit is linking with the circuit itself or the circuit 1 itself or the coil 1 itself. Then that is called the self inductance. Then some amount or the amount of the flux which is linking with the secondary winding or the secondary circuit. So due to the flux linkage linking to the secondary winding, due to the change in current in the primary winding, so there will be an EMF induced in the secondary winding. Then how to calculate that EMF induced in the secondary winding due to the change in current flowing through the primary winding, that we are going to find in this today's class. So this equation already we know, okay, E2 is equal to M into dI1 by dt. So here M is the mutual inductance between the two coupled circuits, and here I1 is the current flowing through the primary winding, right? So that's what I told you. Okay, so how the EMF is induced in the secondary winding due to the change in current in the primary winding. So the cause to produce the EMF in the secondary winding is the change in the current in the primary winding. So that's why here di by dt. Okay, of course here the EMF not only depends on the di by dt, it is also depends on, okay, so how these two are coupled with each other. So that means that represents the mutual inductance between the two circuits, right? So this is how the E2, which means the EMF induced in the secondary winding or the secondary winding, which is equal to M into dI1 by dt. Then here, suppose let us consider if I1 is the sinusoidal current, okay, then we can make it as a I1 is equal to Im sin omega t, that we know I1 M sin omega t, right? Then this E2 will become M into d by dt into I1 M sin omega t, right? So or in another words, we can write, just apply the differentiation to the sin omega t, then this equation will become M into omega I1 M cos omega t, right? So just again I'm going to convert this cos omega t into the sin omega t. So we can write the cos omega t, okay, in terms of sin omega t plus 90 degrees, right? Then here this one we can make it as, because here j means here it is the cos omega t. So we can rewrite this one cos omega t as a j sin omega t in the complex form. Then substitute in place of cos omega t the j sin omega t. Okay, so then the equation which is the EMF across the secondary winding E2, which is equal to J omega M I1 M into sine omega t. Okay, so which means again here this I1 M into sine omega t. Just we are simplified to get into the standard form, right? But here one more thing that we need to remember here it is, then finally we can write this one as, okay, because here which means I1 is equal to, we know already, so wherever this I1 M sine omega t is there, you just replace this with this I1, then this equation will become finally E2 is equal to J omega M I1, okay, J omega M into I1, right? So this is the final equation for the EMF induced across the secondary winding of the coupled circuits. So the same principle we usually apply in the transformers, right? Yeah. Then there are two conditions here. Okay. So this is in the general case that we are considered. Okay. So here the two cases are, the first case is when the secondary is the open circuit. If the secondary is open circuit, then what is the EMF induced across the the secondary winding? Because of course here we have already calculated, we are considered the same thing, but here just the standard form or the simple form we have calculated. So here we didn't consider the inductance of the coil 1 or the inductance of the coil 2 and all. Okay, but here by considering the self-inductance of the coil 1 and coil 2, so how we can calculate the EMF induced in the secondary winding, right? So for that here, just we are going to apply first the KVL to the primary circuit. So this is the primary circuit, okay, or circuit 1 and circuit 2. So the primary circuit is nothing but the circuit 1. If you apply the KVL here, then it is very simple, so that we will get E1 is equal to I1 into R1, because here I1 is the current flowing through this particular circuit, and plus L1 into dI1 by dt, right? Because the E1 is equal to the total voltage across these two terminals. So the total voltage across these two terminals is equal to the sum of the voltage across this resistive load and the voltage across this inductive load, right? So which means VR and VL. So which means here it is representing VR and here it is representing VL. We know already VR is equal to I1 into I into R and VL is equal to L into di by dt. So here the current I is we are considering as a I1, which is flowing through the primary circuit, right? Of course, in the secondary circuit, the current flowing through is 0, because we just considered the secondary as a open circuit terminals, right? Then after that, the same concept that we have applied in the general case here also, which means of course if I1 is sinusoidal, then definitely the E1 will become also the sinusoidal. So that's why here if E1 and I1 both are sinusoidal, then this equation will become, wherever I1 is there, you just substitute I1 as a I1 sine omega t, right? So E1 is equal to I1 plus R1 plus L into di by dt. In the place of I1, we are just substituting I1 M sine omega t, right? The same way, okay. So here if you apply the differentiation, then this will become the cos omega t, then the equation will become I1 R1 plus L1 omega I1 M into cos omega t. The same way again, the cos omega t is equal to sine omega t plus 90 degrees, okay. So then we can make it as a cos omega t is equal to j sine omega t. So the same thing here we are substituting, okay. Then this equation will become I1 R1 plus L1 Wj I1 M sine omega t. So the same way here, let me take okay, yeah, finally the equation will become like this. If you take I1 as a common, because here as we know, because okay, yeah, then this equation will become E1 is equal to I1 R1 plus j omega L1, I mean I1 L1 is equal to, so here if you take I1 as a common, then this equation will become I1 into R1 plus j omega L1. So actually why we are calculating all these things means here now we need to find I1 here actually, okay, right? So then I1 will become E1 by R1 plus j omega L1, right? Then, but actually we know the another equation that we have derived derived here. So that is E2 is equal to j omega m into I1. So from this we can find again I1, right? So from this equation here I1 is equal to E2 by j omega m. Then here E2 by j omega m, this is also I1. I1 is equal to E1 by R1 plus j omega L1. So here this equation 1 and this equation 2 both are representing the same I1, so that we can equate equation 1 equal to equation 2. So here by equating these two equations, then this equation, okay, this will become, so of course from equation 2 here it is E2 by j omega m, and from this equation 1 here it is E1 by R1 plus j omega L2. So which means here we are going to find E2 in terms of the other parameters. Okay, now because here we don't know what is the mutual inductance, right? That's why, so because in the previous place we calculated E2 in terms of mutual inductance. But here if you don't know mutual inductance, then how you can find the E2 value? So that's why here we are deriving this equation. So if you simplify this, then you will get the E2 value. E2 is equal to j omega m E1 by R1 plus j omega L1. Right? So which means here the voltage across the secondary winding, it is not only depending on, because of course, because in the previous cases, if you know the I1 value, then only we can able to find, right? But in this case, okay, if you don't know the I1 also, you can find the value of E2, right? Because we eliminated I1, okay, so that we can find the E2 also here. So then E2 is the voltage across the secondary winding. Then E2 is equal to j omega m E1 by R1 plus j omega L1. So this is another equation, right? So because of course this equation we already know, because we have derived in the previous classes, but this equation is new equation, so we have to remember. So j omega m into E1 by R1 plus j omega L1. So you know what is m? M is the mutual inductance between the two coupled circuits, and E1 is equal to the EMF of the voltage across the primary winding, and here R1 is the resistance of the primary winding, and L1 is the inductance of the primary winding, or the self inductance of the primary winding. So we have calculated this one with in terms of the primary winding parameters, right? Then based on this concept, let me just I'm trying to solve some basic problem. So let me read the problem. For the circuit shown in this figure, determine the potential difference E2 which appear across the open circuit secondary winding. Of course, here they have given the condition. It is open circuited secondary winding. Then given that E1 is equal to 8 sine 2500 t volts. Okay, so find the E2. Of course, this circuit is similar to the previous circuit that which we have considered to find the E2 in terms of the primary winding parameters. So we can directly take the equation and you can substitute, because here you know what is E1. So here E1 is equal to 8 sine 2500 t. Okay, and R1 is equal to 15 ohms and L1 is equal to 5 millihenries, right? Of course, here R2L2 is there, but we doesn't require R2L2, and of course M is also there. M is also they have given 0.1 millihenries. Then we know the equation. Okay, so substitute all these values in this equation. Then you can find the value of the E2. Okay, so then here either ways you can find the value of E2. Okay, one is just by simply j omega m into I1. Okay, because here there is a scope to find I1 here, because I1 is equal to E by Z1. Here this is the Z1. Okay, so Z1 Z1 is equal to, here Z1 is equal to R plus JXL, right? R plus JXL. So that's why here this is what is that, the omega value. So j omega into L, because XL is equal to j omega into L. So here omega value is, because here it is sine omega t in the form of sine omega t. Okay, so here omega is equal to 2500. So that's why here j into 2500, and this is omega and this is L. So L is 5 millihenry. So 5 into 10 to the power of minus 3. So this is what here R plus J omega L1. So here omega L1 is nothing but here it is actually J is already there. So XL, right? So the inductive reactance XL is nothing but, right? So this is how we can find the Z1 value. Then I1 is equal to E1 by Z1. So you know the I1 value and you know the M value. Then you know the omega value also. Directly you can substitute in this equation. Then you can find E2. Otherwise, okay. So without finding I1 also, there is another equation that we have derived just now. So you just substitute J omega M value and E1 value R plus J omega L1. Again the same values. So you will get the value, okay, so which is then the EMF induced in the secondary winding, okay, are the potential difference E2 which appear across the open circuited secondary winding, which is 0.102 at an angle of 50.19 degrees volts, right? So this is how we can find the value of the E2 when we know the primary winding parameters, right? Then coming to the problem 2, here the two coils X and Y with a negligible resistance have a self-inductance of 20 millihenries and 80 millihenries respectively, which means of course X and Y coil, so that's why we should consider LX is equal to 20 millihenries and LY is equal to, here it is 80 millihenries. And the coefficient of coupling between them, of course here there is another concept, coefficient of coupling, that we have discussed already. So coefficient of coupling K is equal to 0.75 that they have given. If a sinusoidal alternating potential of 5 volts is applied to X, which means here it is EX, which is equal to 5 volts, then determine the magnitude of the open circuit EMF induced in Y, which means we have to find the value of the EY. What is EY? The same equation here also we can use. Okay, but here the thing is, in this equation, this is the equation, but in this equation you don't know the value of M, right? Then of course we know because in the previous classes we have discussed the concept of the coefficient of coupling. So we know the coefficient of coupling, but we know the equation also here. M is equal to K into square root of L1 and L2. So here K we know the value 0.75, and here L1 means of course L1 is nothing but here LX and L2 is nothing but here LY, because instead of 1 and 2 coils, so here they have considered the coil X and coil Y, right? So that's why here just substitute all these values, then you will get here what is that, the mutual inductance here it is 0.03 amperes. Then after that, of course, direct equation or direct formula, you just substitute, okay. But here anyway, in this case Rx, which means in a standard form it is R1. Here they mention like with negligible resistance, okay. So which means here Rx is equal to 0. So that's what here R1 or Rx is equal to 0. Then this equation will become J omega M into Ex by J omega Lx. So anyway, J omega gets cancelled. Then this equation will become M into Ex by Lx. So M, you know, 0.03 and Ex is equal to 5, which is the voltage across the coil X, and Lx, which is the inductance of the coil X, right? So which is 20 millihenry. So if you substitute all these values here, then you will get finally the value of the EY, which means the potential difference or the voltage across the coil Y, which is 7.5 volts. So this is how we can find the induced EMF in the secondary coil by using this equation. So then coming to the second concept. So the secondary terminal having a load impedance. In the first concept is the secondary terminal is the open circuited. But if you connect some load impedance across the secondary coil, then what is the EMF induced across the potential difference across the secondary coil, that we need to find here. Of course, here the concept is the same way that we are going to apply. So first just apply the Kirchhoff's voltage law to the primary side. Okay, so for that, here we have just applied I1 into, okay, because here one thing that we need to remember here, it is E1, okay. So because Here the load terminal is there. I mean, the secondary circuit is not open circuit. So that's why some amount of the current will flow through the secondary winding also, which is I2. Right. So that's why here E1 is equal to I1 into R1 plus J omega L1 plus or minus J omega Mi2. This concept we have already discussed. Right. But here plus or minus, so we don't know plus or minus. Of course, when we will get to know plus or minus, because based on the the direction of the currents flowing through each coil. Okay, whether the currents entering to the each coil is in the same direction or not. Okay, so which means whether the flux produced by these two coils is in the same direction or not. If it is same direction, then here you will get the plus sign, and if it is opposite direction, then you will get the minus sign. That we have already discussed in the dot conversion also. Dot convention concept also, right? Yeah. Then here the same thing again, apply the Kirchhoff's law to the secondary winding. Then here this will become, okay, initially let us consider, because we don't know the value of the voltage E2. Okay, so that's why initially we are just considering it as a 0. So then I2 into R2 plus J omega L2, because here L2 and this is R2, and plus or minus J omega M into I1, because some amount of the current will flow, I mean some amount of the voltage will produced across the secondary winding due to the current flowing through the primary winding. The same way as in this equation number 1. So let us consider this is equation number 2, right? Then from this equation number 2, we can find the value of I2, which is equal to plus or minus J omega I1 by R2 plus J omega L2. Then after that here, substitute this I2 value that we have calculated from the equation number 2 in equation number 1, right? So which means substitute I2 value in E1. Then here E1 will become, of course, the first term is as it is, because the first term is related to the parameters referred to the primary side. So which is I1 into R1 plus J omega L1 plus or minus J omega M into. So in the place of I2, we are substituting the value of I2, which we have calculated from the equation number 2, which is J omega M1 by R2 plus J omega L2. Then here, when coming to the E1, okay, and if you simplify this, so how we can simplify? Of course, here J is there and here J is there. Okay, so J into J square, so the J square will be equal to minus 1, that we know already. So substitute minus 1 here. Okay, so that anyway, suppose if it is minus, then it will become plus. Let us consider the value as a plus. Then here E1 is equal to, if you take I1 as a common, because in this term I1 is there and here I1 is there. If you take I1 as a common, then this equation will become I1 into R1 plus J omega L1 plus omega square M square by R1 plus J omega L2. Right. So here what I am going to do, just for simplifying this equation. So here I am multiplying. So I am multiplying the numerator and denominator by the term R2 plus J omega. Sorry, R2 minus J omega L2. R2 minus J omega L2. So if you multiply R2 minus J omega L2, so here already the term which is R2 plus J omega L2 is there. Okay, so which means here A plus B into A minus B, which is equal to A square, okay, minus B square, right? So which means here A is equal to R2 and here B is equal to J omega L2, right? So here R2 means here R2 square minus, okay, so here J square omega square L square. So here J square means again minus 1. So minus of minus plus, then here it will become R2 plus omega square into L2 square. So this is what here this, right? So again, because we are multiplying the numerator and denominator with this term, so numerator again this term is as it is written. Then if you furthermore simplify, then this equation will become like this, right? So just we are trying to simplify this equation furthermore. So finally you are getting the, because here just take this E1 to the left hand side, because already left hand side E1 is there. So it will become E1 by I1. So E1 by I1, or which is also called as the effective primary impedance, which is we usually representing it as a Z1 effective, which is equal to R1 plus, because we are just separated the real term and the imaginary terms. So the real term here it is R1 plus omega square m square r square by R2 square plus omega square L2 square plus j into the imaginary term, which is omega L1 minus omega cube m square L square by R2 square plus omega square L2 square, right? So this is called as the effective primary impedance, right? So which means here actually this is in terms of R1 plus j omega L1, R1 plus j omega L1. So then this is known as the reflected impedance. The reflected impedance, it is called as the reflected impedance, since it represents the impedance reflected back into the primary side by the presence of the secondary current, right? So this is the reflected impedance. Okay, why it is called as a reflected impedance? Because it is reflected back into the primary side by the presence of the secondary current, due to the secondary current. So that's why this is called as the reflected impedance, right? Then of course here the reflected impedance, if you furthermore what is that, simplify this reflected impedance, okay, then finally we can make it as the reflected impedance ZR is equal to omega square m square by Z2. This is called as the reflected impedance, right? So this is how I mean, of course, based on this reflected impedance also we can solve some numerical problems, okay? So that we will discuss in the next class, right? Because here, because we know already how to find the EMF produced in the secondary side, okay, when there is a open circuit. Of course, when there is a impedance also we can find the same by applying the same concept, but here there is another concept which is called the reflected impedance. So here our main aim is to find the reflected impedance in the secondary winding, right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.